To determine whether a particular complex number S or a point in the complex plane is a root of the characteristic polynomial or characteristic equation, or the point is on a root locus or a branch of the root locus, we saw that there is a condition or a criterion known as the argument or the angle condition or criterion, which can be used, and which, if you remember, states that a point S is on the root locus if the sum of the angles subtended by this point at the poles minus sum of the angles subtended by the same point at all the zeros, this difference of the two sums is either 180 degrees or pi radians, or plus minus 2k pi radians, that is plus minus a multiple of 360 degrees. This is called the angle condition. So whether a given complex number S or the corresponding point is on the root locus or not depends on whether this condition is satisfied or not. And I had asked you for our particular problem to find out whether the point S equal to 2 plus J2 can be on the root locus. To determine if the point S is on the root locus, then to determine the value of the gain k, for which it will be a root of the characteristic polynomial, we use the second fact, namely the product of the lengths of vectors drawn from the poles to S divided by the product of lengths of vectors drawn from the zeros to S. This equals the gain Ka. Now the angle condition or criterion may appear to be a little complicated, and at first glance it seems so, but let me remind you once again that the subject of control theory in particular and electrical engineering in general does make use of quite a few mathematical ideas or concepts. So if one wants to be in any branch of electrical engineering, even if it involves a lot of hardware, for understanding electrical engineering, its principles, it is necessary to be familiar with some of the mathematical concepts or techniques, more so in the case of control theory. For example, by this time it should be absolutely clear to you that differential equations, at least the simpler ones, linear differential equations with constant coefficients, similarly Laplace transformation, complex plane, complex arithmetic, pole zero diagram, transfer function, these are all concepts which are going to be extremely useful in dealing with control theory problems. However, that particular rule that I was mentioned, namely a point on the real axis belongs to the root locus under such and such condition, that can be obtained more simply without using the angle condition, and it goes like this. I am mentioning this because you should know various alternative ways of getting at results. So here was our example. We had some poles minus 1, minus 3, minus 4, two zeros, 2 and minus 2, and we are trying to determine whether a given point is on the root locus or not. Now if one looks at it from the same viewpoint as the angle condition, remember that we had written it as, for a particular example, S plus 1 into S plus 3 into S plus 4 divided by S plus 2 into S minus 2. This was going to be equal to minus Ka, and Ka being positive, this was to be negative. So the point S was on the root locus if this was true. Now instead of thinking of S as a complex number, because we are going to look at portions of the real axis which may belong to the root locus, so in other words we are only going to look at S which are real numbers, points lying on the real axis, and we want to determine whether this condition is satisfied. Now look at the right hand side. The right hand side is a negative number, so what this condition says is that this product should be a negative number, right? Now when S is a real number, each one of these, S plus 1, S plus 3, S plus 4, S plus 2, S minus 2, each one of them is a real number. Only when S is complex, like for our problem S equal to 2 plus J2, then each one of these factors becomes a complex number. But if S is a real number, then each one of these factors, S plus 1, etc., are all real numbers. If they are real numbers, they can be either positive or negative or 0. So suppose we choose S such that none of the factors is equal to 0. In other words, we don't choose S as either a pole or a 0. So on the real axis there are some poles and zeros, we will exclude them. We will choose points other than the poles and zeros on the real axis. In that case, each one of these factors is either positive real number or a negative real number. Fine. Now s plus 1, look at the factor s plus 1. When will s plus 1 be positive? S plus 1 will be positive when s plus 1 greater than 0 or s is greater than minus 1. So if I show on the real axis, here is the point minus 1, which in our problem was a pole, then for what s on the real axis will s plus 1 be positive? S which are to its right, here, here or anywhere, s plus 1 is positive, s greater than minus 1 on the real axis. So these are points to the right of minus 1. So s plus 1 is positive for s greater than minus 1, s plus 3 is positive for s greater than minus 3, s plus 4 is positive for s greater than minus 4. Similarly for the two factors in the denominator. So the signs of each one of these factors will depend on whether the point s is to the right of the particular pole or 0. This is the first observation. Now secondly, if you have complex poles, then as I mentioned several times, they occur in conjugate pairs. For example, if 2 plus j2 is a pole, not in our problem, but suppose in some situation, then we have a factor s minus 2 plus j2 and we have another factor s minus conjugate of this, which is 2 minus j2. Now this can be rewritten as s plus 2 plus j2 into s plus 2 minus j2. Now it's easy to see that this thing is s plus 2 square plus 4. Now for s real, s plus 2 is real, s plus 2 square is real, positive or 0, s plus 2 square plus 4 is greater than 0. So when you have a pair of complex conjugate roots like this, the corresponding two factors for s real will always be positive, and you can verify that this holds no matter where the poles are or where the two roots are, the conjugate roots are, whether they are in the left half plane or right half plane or on the j omega axis. So long as they are not on the real axis and therefore they are truly complex, the product of the corresponding two factors is always positive. Alright. Now let us go back to our example. So here we have a number of factors in the numerator, a number of factors in the denominator. The factors which correspond to the complex poles and complex zeros we need not worry about, because their product will always be positive no matter where the point s is. So now what will be the sign of the numerator? S plus 1, s plus 3 into s plus 4. Each one of the factors is either plus or minus, and it's plus for points s which are to the right of the corresponding root. S plus 1 is positive for s to the right of minus 1, s plus 3 is positive for s to the right of minus 3, similarly for s plus 4. S plus 2 is in the denominator, that is positive for s greater than minus 2, s minus 2 is positive for s greater than 2. So from this it's easy to see that if we have a point which is to the right of all of them, here was the point that we looked at yesterday, then each one of the factors s minus 2, s plus 1, s plus 2, s plus 3, s plus 4, each one of them is positive. So when we take the product and divide by the other product, this whole thing on the left hand side will be positive. But for the point to be on the root locus, it has to be equal to minus Ka or negative. Therefore this number or that point cannot be on the root locus. So this point cannot be on the root locus. Now it so happens that the location of the point is such that the number of poles and zeros to its right is 0, and we treat 0 as an even number, so it's not an odd number. Now let's move to this region between these 2 points. Now what is the situation? There is a factor now corresponding to this s plus 2, s minus 2, which is positive. All the other factors are negative. Now this is where you have to look at the rule and get the correct conclusion that if the number of poles and zeros to the right is odd number, then the point will belong to the root locus. I leave it to you to work it out from this point of view and make sure that the rule as we had stated is correct. Evans, when he stated the rule, looked at the angle condition. In fact, he gave a number of additional rules, many of which make use of the angle condition, and so the angle condition is very important, but you don't always have to use that angle condition. You can use, for some simple facts like position of points on the real axis, you can use some simpler arguments. And I have given you an example of one such simpler argument. I stated that the root locus starts at the poles, it ends at the zeros, but how does it proceed from the pole to the zeros? And I had concluded yesterday, and I showed it to you, that this particular branch of the root locus starts at -1, ends at 2, but goes along the real axis as I have shown. Now how do I know that? So for that there is a rule which comes about by the use of the angle condition, and that rule concerns what is called angle of departure. Let us say here is a pole, so I know that a root locus branch will start from there, that is for k very small there will be a root very close to this point. So there will be a root locus branch which starts at that point, but how does it proceed? Will it go like this? Will it go like this, like this, like this? For very small k, it can be approximated by the tangent to the root locus, so it can be thought of as a small straight line, but which direction? In which direction does the root locus branch take off? That direction is determined by the corresponding angle which is called the angle of departure. Angle of departure from the poles of the transfer function, or the poles on the pole 0 diagram. Likewise, there will be angle of arrival at the zeros. For example, here is a 0 that we had at 2. Now we know that for very large k, there will be points on the root locus which are close to this location of the 0, and therefore as k increases beyond any limit, that is, as we say k tends to infinity, the root locus branch will end up being at the 0. But in which direction will it approach or arrive at the 0? Now that direction or the corresponding angle is called the angle of arrival. Now using the angle condition, namely sum of angles at the poles minus sum of angles at the zeros is an odd multiple of pi or 180 degrees, using that condition for points very close to the pole or to the 0, apply that condition, you can find out the angle of departure and the angle of arrival at the poles and zeros respectively. It will take some time to go through the derivation of the rule, but you can look it up, and it is a fairly simple rule about the angle of departure and the angle of arrival at the poles and zeros. It does involve some calculation of angles made by various vectors that one has to draw, but that calculation is not a very complicated calculation. It is essentially you draw vectors and find out the angles made by them with the positive real axis. One can either measure them if one plots the poles 0 diagram, or one can calculate them with the help of the calculator without any difficulty. So the angle of departure and the angle of arrival can be calculated using that rule, and that is the rule that would enable you to check that in our example the root locus branch which leaves at -1 goes in the direction of the positive real axis, and therefore the assumption that it goes along the real axis is a good one. Similarly, the branch which arrives at -2 arrives at it from the negative side of the real axis, so that part is okay. Further, we know that all the points between these two are on the root locus for some value of k or the other, and therefore it is a reasonably good conclusion that this whole segment of the real axis is on the root locus. Not only that, it is a branch of the root locus. As I told you, the root locus method is a what may be called a qualitative method. It is more a qualitative method for getting some knowledge or making some good guess about what is going to happen. It is not a substitute for calculations. When calculations are required, calculations will have to be made. Even when plotting the root locus, one will have to make some calculations. So it is not that calculations can be entirely avoided, but qualitatively doing very few calculations or very simple ones, by looking at a figure, by looking at a pole 0 diagram, by imagining various situations, one can work out or figure out quite a bit about the root locus, and that is the beauty of it. It is mainly a qualitative tool, and therefore it is useful for use by human beings, not by computer programs. And so I repeat that for us to solve simple small problems, or even problems which are not so small, to get some qualitative idea, the root locus method is a good method, and therefore one should learn it. It is not a substitute for quantitative investigation. But quantitative investigation or using a program package is not a substitute for understanding. It's not a substitute for thinking about what can happen, what will happen, or what cannot happen. The Laplace transformation, the root locus method, Nyquist criterion, which we are going to look at, all these are helpful tools for getting an understanding of what's going on rather than for finding out exactly what is happening. All right then, so we have how many rules so far? We have the rules that for small k, the root locus is near the poles, so they start from the poles. For large k, they are near the zeros, so they end at the zeros. Then I have talked about asymptotes, and I will state a rule about the number of asymptotes and something more about them. Real axis portion of the root locus I have discussed in detail. Angles of departure from the pole, angle of arrival at the zero. I have just mentioned that there is a rule which uses or based on the angle condition, and you should look up that rule from your textbook. Now let us look at the asymptote, the rule about asymptotes. Now there will be asymptotes only in the case when the number of poles np is not equal to the number of zeros nz. If a transfer function or if a pole zero diagram has the same number of poles and zeros, then there are no asymptotes. That is, there are no branches of the root locus which either go away, move away towards infinity as we say, or start from positions which are very far off and then come towards the finite part of the complex plane. So there are asymptotes, that is something of that sort happens going away to infinity or starting from infinity only if np is not equal to nz. The number of poles is different from the number of zeros. So if the two are equal, there is no need to worry and think about asymptotes, there are none. Now np not equal to nz, there can of course be two possibilities. One is the number of poles is greater than the number of zeros. If this is so, then the number of root loci is the larger of the two, it is np. So all the root locus branches will start at the poles, nz of them will end at the zeros, and the remaining will go towards or approach asymptotes, that is go towards infinity, that is increase in absolute value, maybe with a change of angle as k increases. So there will be asymptotes for the case when np is greater than nz. There will be nz branches which end at the zeros and the remaining branches will go off asymptotically. In the other case, when np is less than nz, it is going to be just the opposite. The number of branches of the root locus is the larger of the two, that is the degree of the characteristic polynomial. Therefore there will be nz branches, there are nz zeros, so nz branches will end at the nz zeros, but there are only np poles. So np branches will start at poles, the remaining, the difference between the two, will start from a very region which we refer to as the region at infinity. That means for small value of k, there will be roots which are very large in absolute value. That is what we mean by saying that the roots or the branches start from infinity. Now one can show that in such a case, when np is not equal to nz and therefore there are asymptotes, the asymptotes can be actually located. That is, one can actually find out the asymptotes for the branches of the root locus which either approach them as k increases, that is go away as k increases, or start for k small, that is come towards the finite part of the plane as k increases from 0. Now the location of these asymptotes can be calculated by a rather simple rule. Of course the proof of it is a little complicated, so we won't look at that. And the rule is simply this: first do the following. Just calculate the number given by, I am going to write here sigma p, by that I mean the sum of all the poles, whether real or complex or imaginary, sum of all the poles. From that subtract the sum of all the zeros. So compactly sigma p minus sigma z, sum of all the poles minus sum of all the zeros. Divide this by the difference between the number of poles and the number of zeros. So np minus nz. In some books np itself is denoted by p nz is denoted by z, and therefore it will be p minus z in the denominator. Don't worry whether np is greater than nz or np is less than nz. Don't worry about the sign of the denominator. Take it, if you have sigma p minus sigma z, into the denominator you will have np minus nz. Now this gives you a number and therefore a point on the complex plane, which is what is called the point of intersection of the asymptotes. Sometimes it is also referred to as the centroid of the pole 0 diagram. This gives you the point of intersection of the asymptotes. That is, if there are any asymptotes, then they all pass through this point. Let us apply that to our particular example. There we had poles at 3 points. The 3 poles were -1, -3 and -4. These were the poles. There were 2 zeros. One was at -2, the other was at +2. So there are 2 zeros. So what is sigma p? Sigma p in this case is just -1, -3, -4, some of them. So that's -8. What is sigma of the zeros? -2 and +2, therefore 0. So sigma p minus sigma z divided by np minus nz in this case will be equal to -8 minus 0 divided by np was 3 poles, nz was 2 zeros, so 3 minus 2. So this is equal to -8, or as electrical engineers will prefer to write it as -8 plus j0. So this is the point of intersection of the asymptotes. The point is on the real axis, on the negative real axis is the point -8 plus j0. So that's one information about the asymptotes. The asymptotes are all straight lines passing through this point. That is another point of information. What about their number? How many asymptotes? np minus nz if np is greater than nz, and nz minus np if nz is greater than np. That is, whatever number either go to infinity or start from infinity. It's the difference between the number of poles and the number of zeros. In our problem, np minus nz is 1. So that means there will be only one asymptote. And because np is greater than nz, this asymptote is what the root locus branch will approach as k increases. So in other words, as k increases, one branch of the root locus will go close to this asymptote or will approach this straight line asymptotically. I hope you remember in coordinate geometry the concept of asymptotes. For example, the hyperbola given by xy equal to 1 has the x-axis and the y-axis as its asymptotes. That is, the branches of the hyperbola are one part of it and the other part of it approach these two axes as one moves along the hyperbola in one direction or the other. Alright, so there is going to be only one asymptote. It's going to pass through this point. Now, in order to specify a line in the complex plane, if I have a point, that's not enough. There are hundreds of thousands of lines that pass through this point. So what do I need to know? I need to know the angle made by a line or a ray with the positive real axis. Now that's precisely what we can obtain. So this will be then the angle made by an asymptote with the positive real axis. Now what is the formula for that? The formula for that is as follows. Take the number pi radians as radians, that is angle, or alternately 180 degrees as an angle. To that, if necessary, add multiples of 2 pi or alternately multiples of 360 degrees. Now whatever this number is, divide it by the difference between the number of poles and the number of zeros. Alright, in our problem, so I start with pi equal to 180 degrees and I divide it by the difference between poles and zeros. So divided by 1. So what do I get? 180 degrees. So that is an angle made by one of the asymptotes. Now I said take 180 degrees and add to it a multiple of 360. So let me add 360 degrees, divide by 1. What do I get? 540 degrees. But a line which makes an angle of 540 degrees is the same as a line which makes an angle of 180 degrees. So this is the same in that sense as 180 degrees. And indeed, therefore, because there is only one asymptote, so the angle made by the asymptote is 180 degrees with the positive real axis. With this then, we can sketch the asymptote as to where it must be. So here is the point -8 plus j0, say. from here draw a ray which makes an angle of 180 degrees with the positive real axis. So what can it be? Here is the angle of 180 degrees, therefore it must be this. And so this is the direction of the asymptote, and indeed if we go back to our problem, you will see that from this pole at -4 I had drawn a branch which was simply going away towards the negative part of the real axis. So I was thinking of the rule about the direction of the asymptote when I drew it this way. Now that I have told you, we can use this rule anytime you want. 180 degrees plus minus multiple of 360 degrees divided by the number of asymptotes. That gives you the angles made by the asymptotes. If there is only one asymptote, there will be one angle. If there are two asymptotes, there will be two angles, and so on. Let's see. Suppose there are two asymptotes. Then what is my rule now? I said 180 degrees divide by 2. So I divide by 2. What do I get? 90 degrees. So I get one angle. But there are two asymptotes. Why 2? Because the difference between the number of poles and zeros is 2. So what is the angle made by the other asymptote? Well, in addition to 180, I can now consider 180 plus 360 and divide by 2. Now I get an angle which is 270 degrees, which is not the same as 90 degrees. So I get two different angles. So if there are two asymptotes, the angles made by them will be 90 degrees and 270 degrees. If there are three asymptotes, what will be the three angles? Think about it. 180 degrees by 3 is 1, so 60 degrees. 180 plus 360 divided by 3, so 180 degrees. And the third one, 180 plus 720 degrees divided by 3, so that is 300 degrees. So the three asymptotes will make angles of 60 degrees, 180 degrees and 300 degrees. Or if I show them on this diagram, then one asymptote will go away like this. The other asymptote, if the center of a point of intersection is the origin, another asymptote will go like that. The third asymptote will go like this, and between each other they will make angles of 120 degrees. So the number of asymptotes is the difference between the number of poles and zeros, and the angles made by them with the positive real axis can be found out by this rule. In our problem, there is only one asymptote, and that asymptote goes towards the negative real axis by this rule. The point of intersection of the asymptote can be obtained by the rule sigma poles minus sigma zeros divided by number of poles minus number of zeros. All the poles, whether real or complex or imaginary, all the zeros have to be included in those summations. Sigma p minus sigma z divided by p minus z is the rule for the location of the common point of intersection of the asymptotes of the root locus. There are some further properties, some of which are so simple that as soon as I state them, you will agree that they are true. The characteristic polynomial, let me go back, looks like what we had: gd of s, hd of s plus ka into gn of s, hn of s equal to 0, right? Now g, h, whether numerator or denominator, have all real numbers as coefficients. Our system parameters like resistance, inductance, back EMF coefficient, coefficient of friction, all of them are real numbers. In fact, most of them are chosen, the concept is such that they are all positive. If I said that a resistance has value minus 20 ohms, then you will suspect that there is something wrong. Either I am talking about resistance in a different way or there is some mistake. But they are real numbers. I do not and I cannot find a resistance which has a value of 2 plus j3 ohms. Notice I am talking about parameters. I am not talking about frequency response, gain, phase or complex gain and things like that. We do come across complex numbers in our work, but the system parameters are all real numbers. So GS, HS, whether D or N, have all their coefficients real. So this whole polynomial is what is called a real polynomial. That is, it's a polynomial all of whose coefficients are real numbers. Because of this, the roots of this occur in conjugate pairs. So not only the poles and zeros, which are the roots of either GD or HD or GN of HN, they occur in conjugate pairs. So in the pole zero diagram, I have symmetry. Symmetry of what kind? Symmetry about the real axis. The pole 0 diagram is symmetric about the real axis. But not only the pole 0 diagram, the root locus plot, that is the root locus branches, the whole figure consisting of all of them, must also be symmetric about the real axis. And why? Because of this fact that points on the root locus are roots of a real polynomial, so they must occur in conjugate pairs. So if there is a point on the root locus above the real axis, there must be a point on the root locus below the real axis, which is like its mirror image in the real axis. So this is called the symmetry of the root locus about the real axis. This is one more rule which follows almost immediately from our knowledge of polynomials. If you think of the example that we had taken, I had said that the root locus will have a branch which will cross the imaginary axis of the j omega axis, and therefore one of the roots of the characteristic polynomial will become 0 for some value of k. So this is called intersection with the j omega axis or with the imaginary axis. Now there is a method for determining the value of k for such intersections and the corresponding location of the intersection. And I mentioned it earlier that there is an algorithm or a procedure which was given by Routh more than 100 years ago. Using that, one can find out the intersections of the root locus with the j omega axis or the imaginary axis and the value of k corresponding to those intersections. Now before I discuss this method based on the Routh algorithm, because the Routh algorithm is not a very difficult one to understand and to use once you have found out what exactly is to be done, and it's a very important tool not only in control theory but also in network theory or system theory. It occurs in investigations of stability, and so every control engineer should know about the Routh algorithm. But there is another way of finding the intersection with the negative, with the j omega axis. That rule is not really very simple to apply, as you will see in a moment, but sometimes it does give you some answers. For example, let's go back to our problem. So let me redraw the figure now, and here are the poles -1, there is a 0 at -2, there is a pole at -3, another one at -4, and there is a 0 at +2. Now I want to find out if any point on the j omega axis or on the imaginary axis will belong to the root locus. So what is it that I am checking? Whether for any point on the imaginary axis, that complex number, in this case the purely imaginary number, will be a root of the characteristic polynomial. Alright. Now we can proceed in two different ways. This characteristic polynomial, I can write down explicitly what it is. So I will do it for our example, and you will see that the situation becomes more complicated if you have a larger number of poles and zeros. I had s plus 1 into s plus 3 into s plus 4 plus ka into s plus 2 into s minus 2. That is the characteristic polynomial. Let us call it p of s, and we are trying to solve the equation or find the roots of the equation ps equal to 0. They are the points on the root locus, the complex numbers s on the root locus, right? Now let's look at this. Now you expand this out and you expand this out. Alright. So if I do that, I'll get what? I'll get s cube plus, from this you can see that I'll get 8s squared plus, there is a way of finding out 3 into 1 plus 4 into 3, 15 plus 4, 19, so 19s plus 4 into 3 into 1, so 12. If you are good in algebra and if you remember it, there is a nice way of multiplying this out mentally instead of writing it down in two steps. S cube plus 4 plus 3 plus 1, so 8s square plus 3 into 1 plus 3 into 4 plus 4 into 1, so that's 3 plus 12, 15 plus 4, 19. The last term is 1 into 3 into 4, so 12, plus ka into, this is easy of course, s plus 2 into s minus 2 is s squared minus 4. Now what is it that I am looking at? I am trying to find out if a purely imaginary number is on the root locus. A purely imaginary number is j omega, for omega real. So I am trying to find out whether j omega is a root of this polynomial, or j omega will make this equal to 0. Now you can see what is going to happen. There are terms like this s squared and there is this constant. When I put s equal to j omega, they will become purely real. On the other hand, there are terms like this s and this s cube. So when I put s equal to j omega, they will become purely imaginary. And so the left hand side can be written as one purely real expression plus another purely imaginary expression equal to 0. Let me do that. The purely real thing, where am I going to get it from? 8s squared, s equal to j omega. So what will be 8s square? With little practice, you will be able to see immediately that it will be minus 8 omega square. Then I have plus 12, which is real. From here, Ka is real, s squared is minus omega square. So this is the real part of the left hand side at s equal to j omega. And what will be the imaginary part? It will be given by j times what? S cube. S cube, s equal to j omega. So j omega into j omega into j omega. How much is that? That is minus j omega cube. So pulling that j outside, I will have minus omega cube. S is j omega. So from here I will get plus 19 omega, and that's all. From the real part, I missed out this term, not only minus omega square but also that minus 4. So this whole thing is equal to 0, right? This is my equation. Minus 8 omega square plus 12 plus Ka into minus omega square minus 4 plus j times this is equal to 0. Therefore, each of the two parts must be equal to 0. The real part must be 0 and the imaginary part must be 0. So from this, I will get two equations, and these equations will be minus 8 omega square plus 12 plus Ka into minus omega square minus 4 equal to 0. That is one equation. The other equation is minus omega cube plus 19 omega equal to 0. Alright, I get two equations. And what are the unknowns? Omega is unknown. I am trying to find out what point j omega is on the root locus. I do not know what omega is, and I do not know the value of Ka for which it is a point on the root locus. So there are two unknowns, there are two equations. This is what is going to happen in general. I take the characteristic polynomial, expand it out, replace s by j omega, separate the left hand side into two parts, the real part plus j times another part, and equate the real part and the imaginary part to 0. I will get two equations for the two unknowns, the gain Ka and the point omega corresponding to that point. I will not call it frequency, although it can be given an interpretation of frequency as we have seen earlier. Now, in general, it may not be immediately clear how to solve these two equations. In this case, for example, it is easy because in the second equation K is not appearing at all, but that may not happen. There will be Ka in the second equation also. So both the equations may contain both the unknowns Ka and omega, and therefore you have to use some algebraic trick or manipulation to solve for omega and Ka. But for our particular problem, it is not that bad because this second equation does not contain Ka at all. So what are the solutions of this? Omega cube minus omega cube plus 19 omega equal to 0, or alternately omega cube is equal to 19 omega. What are the solutions? There are two solutions. One is omega equal to 0. Don't forget that. Don't cancel omega, because when omega equal to 0, this is true. 0 is equal to 0. So there is a solution omega equal to 0, and the second solution gives you omega square equal to 19, and therefore omega equal to plus or minus square root of 19. So corresponding to omega equal to 0, there could be a point on the root locus, and corresponding to omega equal to plus minus root 19, that is j plus minus root 19, that is a point on the imaginary axis that could be also on the root locus. Now I have to check the other equation, because the other equation has to be satisfied. The other equation, now omega is known and I can solve it for Ka, and you can check that if I put omega equal to 0, you will get some particular value of Ka. Let me substitute. If I put omega equal to 0, I will get 12 plus Ka into minus 4 equal to 0, or I get Ka equal to 3. Now that is a value which I can accept because it is positive real number. So I found out that for Ka equal to 3, there will be one root, or there will be one point on the root locus. The location is j omega, where omega is 0 or j 0, but j 0 is nothing but the origin of the complex plane. And so for k equal to 3, origin, the point 0 plus j 0 or j 0 or 0 will be on the root locus. And I had shown earlier the root locus branch like this, implying that there will be intersection with the j omega axis, and this is the point where it will intersect. Now what about the other values of omega? I leave it to you to work out. Put omega square equal to 19 or omega equal to plus minus square root of 19, substitute that in this equation and try to find out the value of k. You will find out that the value of Ka that you get will be less than 0, but we are not looking at gains which are less than 0. Therefore, this thing we have to rule out or exclude. So the only intersection that we can have with the j omega axis is at the origin. This will be an intersection if a negative value of Ka was allowed. In some investigations, one does look at negative values of Ka, and the corresponding root locus that is obtained is therefore called the inverse root locus. Normally, when you have Ka positive, one does not call it the direct root locus, you simply call it the root locus. But if you allow or consider the values of Ka less than 0, then we are looking at the inverse root locus. So then it will show that for the invert root locus, there will be a point on the root locus corresponding to omega equal to plus minus root 19. In other words, the point plus minus j root 19 will be on the inverse root locus. Now this is one way of proceeding, but this requires, as you can see, a lot of work. I have to expand the polynomial, replace s by j omega, equate real and imaginary parts equal to 0, solve the resulting two equations for omega and Ka, and choose the values of Ka greater than 0 if they do result. That will give you intersections with the j omega axis. This is one way of doing it. Another way of doing it will look at the angle condition. That will involve, of course, calculation of or writing down expressions for some angles, and from that you can get an equation which only involves omega, but unfortunately it will not be a simple polynomial equation. Using a calculator, however, one can without too much difficulty find out at least an approximate solution for the omega value. That is the second method, but the preferred method is the one that uses the Routh algorithm or the Routh criterion. So we will take a look at the second method for a very quick exposure. I will not talk about it in great detail. I will leave it to you to look it up from your textbooks, what kind of calculations have to be made, but then we will spend more time on the Routh algorithm or the Routh table method for determining intersections with the j omega axis or with the imaginary axis.